All right, so let's get into it. We've talked about the hydrogen atom, but what happens when you stick it in a really strong, uniform electric field? You might think you know, but the answer is, well, it's kind of tricky. In this revision session, we're going to dig into the Stark effect, and we're going to see why the ground state and the first excited state of hydrogen tell two completely different stories. It's a real tale of two states.
Okay, so here's our game plan. First, we'll just set the scene. What's the basic physics of an atom sitting in an E field? Then we'll look at the ground state, and you'll see why I'm calling it a surprise. After that, we'll jump up to the excited states, where everything changes because of degeneracy. That leads us right into how these states mix and the energy levels split apart. And finally, we'll put it all together in a side-by-side recap to make sure it all clicks.
So before we jump into the math, let's just make sure we're all on the same page with the basic setup. We need to frame the problem correctly before we can solve it.
This is the fundamental question, right? We have our nice, simple hydrogen atom, and we're just going to turn on an external electric field. What happens to its energy levels? How do they shift? How does the atom respond? This whole process, this interaction, is what the Stark effect is all about. So formally, what is the Stark effect? It's the change, the shifting, and the splitting of an atom's energy levels when you put it in a static electric field. Now, if you've studied the Zeeman effect, this should sound familiar. That's the same idea, but with a magnetic field. The Stark effect is the electric field version of that.
To actually calculate these energy shifts, we're going to use our good old friend perturbation theory. And for that, we need to define the perturbation itself. That's H prime. So if we align our external electric field, EXT, along the z-axis, the potential energy added to the system is just the charge of the electron, E, times the field times the electron's position, Z. Pretty straightforward.
Okay, let's start with the simplest case you can imagine. The hydrogen atom in its ground state, N equals 1. You'd think this would be easy, but, well, there's a really interesting subtlety here.
So, the ground state is non-degenerate, right? There's only one state with that energy. That's great. It means we can use the easier version of perturbation theory, non-degenerate perturbation theory. And the first-order correction to the energy is just the expectation value of the perturbation in the unperturbed state. In other words, we just have to calculate this integral you see here. And when you actually go and calculate that integral, what do you get? You get a big fat zero. Nothing. No change. To first order, the electric field doesn't shift the ground state energy at all. The atom just seems to ignore it.
So why? Why is it zero? Is that just a mathematical fluke? Absolutely not. In quantum mechanics, when something is zero, it's usually for a deep physical reason. And in this case, that reason is symmetry.
Let's break this down. Think about what we're integrating. The ground state wave function, psi100, is spherically symmetric. It's an even function. It has what we call even parity. But our perturbation, H prime, is proportional to z, which is an odd function. It has odd parity. And if you remember from your math classes, when you integrate the product of an even function and an odd function over a symmetric interval, like all of space, the result is always zero. The positive and negative contributions perfectly cancel out. So what does this mean physically? It means the ground state atom doesn't have a built-in or permanent electric dipole moment. It's perfectly symmetric. So the electric field can't just grab onto it and twist it. What the field can do, though, is slightly distort the atom. It pulls the electron cloud one way and the nucleus the other. This creates a tiny induced dipole moment. But this is a much weaker effect, and it leads to a second-order energy shift that goes as E squared, not E. Okay, that was the ground state. Now let's level up. Let's see what happens with the first excited state, when N equals 2. And I'm telling you, everything we just said gets thrown out the window. The rules are completely different here. So what's the big deal with N equals 2? It's one word, degeneracy. Remember, for hydrogen, the energy only depends on the principal quantum number, N. So for N equals 2, we have 4 states, the 2s state and the 3 2p states, that all have the exact same energy without the field. This fourfold degeneracy is the key to everything that follows. Because we have this degeneracy, our simple, non-degenerate perturbation theory just fails. The math literally breaks down. So we have to pull out the heavy machinery, degenerate perturbation theory. It's designed specifically to handle situations like this. So what does this more complicated theory tell us? It tells us that the electric field is going to break the symmetry. It's going to force the atom to pick a new set of states, and in doing so, it's going to lift the degeneracy.
The first step is to build this perturbation matrix, W. Basically, each element of this matrix, Wij, tells us how the perturbation H' connects state I to state J. And when you calculate these matrix elements, something amazing happens. Most of them are zero. Again, because of symmetry and selection rules. The only states that the perturbation actually connects are the 2s state and the 2pz state. Why? Because they have opposite parity, just like we needed before for a non-zero integral.
Now, the first-order energy corrections are just the eigenvalues of this matrix. And when you diagonalize that simple 2x2 block, you find the shifts. And look at this. We get 3 distinct values. One state is shifted up in energy by 3 exte, another is shifted down by the same amount, and 2 of the states don't shift at all. We have a real, non-zero, first-order shift that is linear in the electric field. This is the linear Stark effect. So what are the states that correspond to these new energies? They're not the original 2s and 2pz states anymore. The electric field has forced them to mix, to form new hybrid states. These are the so-called good states for this problem. And if you look at their structure, they're no longer spherically symmetric. They have a permanent electric dipole moment, which is why they can interact so strongly with the field.
So let's visualize what just happened. Before we turned on the field, we had one energy level, E2, with 4 states living there. We turn on the field, and that single level splits into 3. One state goes up, one state goes down, and 2 states, the ones that weren't mixed, stay right where they were. The degeneracy has been lifted by the field.
Okay, we've been through a lot. Let's put it all on one page and do a direct comparison. This is really the heart of the whole story. This table is what you need to remember. For the ground state, n equals 1, there's no degeneracy. We use non-degenerate perturbation theory, and we find no first-order shift because of symmetry. The physical picture is a weak induced dipole. For the excited state, n equals 2, there is degeneracy. We must use degenerate perturbation theory. This allows the 2s and 2pz states to mix, creating new states that have a permanent dipole moment, and that gives us a much stronger linear energy shift. So, to wrap it up, what are the absolute key takeaways for your revision? 1. The Stark effect is about energy shifts in an E field. 2. For the hydrogen ground state, there's no linear effect because it's non-degenerate and spherically symmetric. 3. For the n equals 2 states, degeneracy is the crucial ingredient that allows for a first-order linear shift. And 4. This shift happens because the field can mix states of opposite parity, like 2s and 2pz, creating new hybrid orbitals that have a dipole moment. And hey, don't just take it from me. Griffiths says it best in his textbook, and I'm paraphrasing a little here, but the core idea is that the degeneracy in the excited state isn't just a minor detail. It is the crucial feature. It's the entire reason the linear Stark effect exists in hydrogen. So I'll leave you with a final thought to chew on. We've seen that degeneracy is everything here. But what about in more complex, multi-electron atoms? In those atoms, the 2s and 2p orbitals often don't have the same energy to begin with. The degeneracy is already lifted. So, based on what we've learned today, what would you predict for the Stark effect in, say, a helium atom? Think about it. Thanks for tuning in, and I'll see you next time.